Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 25, we will continue with routing and scheduling for solid waste vehicles. This is part 2 of the lecture. The different concepts that we will cover. First, we will start with a case study of solid waste transportation model for Asansol. Then we will talk about the distribution problem, vehicle routing problem, optimization techniques for vehicle routing problem. Then we will solve the vehicle routing problem, VRP, and traveling salesman problem in ArcGIS. Then we will use the network analyst module in ArcGIS for explaining traveling salesman problem and the vehicle routing problem. So, as we have discussed earlier that solid waste collection is the most costliest phase of the overall municipal solid waste management system, and as estimated in this particular study, it says that overall collection and transportation disposal of solid waste in India, this is of course done for the year 2006, a little bit older data, but ranges around INR 500 to 1500 per ton. And out of that, 85% of the total expenditure actually goes for the solid waste collection system. So, this study actually talks about the Asansol Municipal Corporation, the solid waste, and it proposes a new collection system for this particular corporation, and it shows us how the collection system is designed. So, I will also explain you that particular proposal that they have given and how they have built that proposal, right. So, then we will explain based on that what sort of algorithms could be used and so on. So, Asansol Municipal Corporation is an industrial town in West Bengal. Area, as you can see, is around 127 square kilometers. It includes 50 wards, 95,000 or almost 1 lakh households, and average household size is around 5. Now, solid waste generation rate for the year 2006 was estimated at 0.25 kilograms per capita per day. Probably this value has increased a bit now, but still it's an acceptable figure. And total quantity of solid waste is around 180 metric tons per day, out of which 120 is domestic solid waste and 60 metric ton is non-domestic. Now, non-domestic means industrial, construction, demolition, and also hospital waste, and usually these are managed by the respective generators, and so these are not addressed in this particular study. So, only this study addresses the solid waste that is generated within the city area, and some from markets, some for complexes, and some from the residential areas. So, total number of bins that are considered is 1350, and these bins are of different sizes that we will consider. And total expenditure is around 2.5 crores. Total supervisors for this particular area is around 20, and total staff is around 487. And this community bin system was initially present over here, and usually during this time around 200 hand carts, 23 trucks and 2 tractors were used for disposal. So, this was the basic system which was at that point of time being utilized, and this study proposes an alternative system which is better compared to what was there earlier. Now, what this study proposed? It proposed different new types of bins and their location instead of standard community bins which was there earlier. Then vehicle types, it also proposed new vehicle types compared to what was there, and also the optimal route for these particular vehicles. Initially the spatial database was created, that is the road network and the bin locations. These were actually put on the map itself, and the location of the landfill site and garage, both of them, one landfill site and one garage is being considered. Now, what kind of bins are considered? There are 3 categories of bins are considered. Door to door is not considered over here. So, C type, so you can see that the bin type A with volume of 7 meter cube, which is thought to serve a population which is more than 300, and it is located at marketplaces, street vendors, locations where there are a lot of street vendors, and the content of C-type bins are actually transported to A-type bin. That means A acts as the secondary storage for garbage collected from C-type bins, and C-type bins are put in slums and other congested areas. That means these are the residential areas where smaller vehicles collect this particular garbage waste and then bring it to this larger bins, so that they could be transported via larger lorries. Now as per MSW 2016, we cannot have this kind of a system. We have to have door-to-door collection, but over here it is stated that it's a community bin level system. That means these bins are provided in close proximity and serves around 200 people approximately for an area. Now we can say that now this kind of system is not relevant, but you have to understand in today's context also there are many places in the city which has got slums and are congested areas where we cannot do door-to-door collection, and there is no other way than to put a community bin over there where people come and throw garbage. So in that case also, if we design a system which is both, we have got door-to-door collection as well as some amount of community bins, in that case collection from the community bins could be brought to the storage points which are the large C-type bins which are provided in places such as marketplaces, street vendors, places where there are a lot of other generators, right. Now B-type bins are present, which is serves around 300 people, volume is around 0.75 meter cube, and the volume, the size C bin is even much lesser, which is 0.05 meter cube, and you can see that these are placed in multi-storied buildings, commercial complexes, community and other private societies, which is also the practice these days. That means this kind of bins are placed over in this kind of societies where the society's garbage come, and from there the municipality collect this garbage. So the frequency of cleaning for A-type bin is daily, whereas the frequency of cleaning for the other two kinds of bin is every 2 days. So that means around 3 times per week, and whereas this is done 7 days or 6 days per week. So the size of the containers that is being decided, it is assumed that the container would be utilized to 50%, and extra capacity is given for unforeseen factors. For example, sometimes there is stoppage of the service because of some issues, or there is extra waste generated during some sort of event. So all these are being considered for this. Like one day people didn't throw garbage, but in the next day, many families came out because of weather and all, they have not thrown the garbage on the earlier day, but in the next day they are coming and throwing the garbage for 2 days. So all these factors are considered as unforeseen factors, and that's why container utilization factor is taken as 50%. 3 kinds of containers as we have discussed: container type A, this is the large container; container type B, this is like those 4-wheeled containers that we have discussed earlier, these are kept for larger generators; and this is container type C, which is in the locally, in residential areas, this kind of containers are kept. And bin locations are based on population density, road width, space availability and distance from a house. So wherever roads are wide, the larger bins are provided; where roads are smaller, then smaller bins are provided. So this is more or less the system this particular study is proposing. Now, to do the study, of course, you have to do the, first we have to code the road network. That means we have to first prepare the road network map. As you can see, the major roads, minor roads and other roads are being marked, and major roads are wider ones, minor roads are the 2.5 to 5 meters, whereas other roads are even smaller roads. So all types of vehicles cannot travel in all roads. So whenever we generate the routes for vehicles and all, we only consider the relevant road network that are acceptable for that kind of vehicle. So similar to 3 kinds of bin, 3 kinds of vehicles are considered, which is and this is done as per the type of collection bin and the road width, in which roads this will travel and what sort of bins they will collect from. So type A is a skipper type vehicle which flies along the major roads. Their length is around 4.5 meter. They take a crew of 2, and usually they lift one A-type bin at a time. Like over here, they have lifted one of the bins, and once it lifts it, it takes it to the disposal site, disposes the bin, and then again brings the empty bin and places it back into that particular area. Then moves on to the next bin. Type B type of vehicle, this is a lifted type vehicle with a front loading mechanism. So over here you can see a back loading mechanism, but this vehicle has got a front loading, that is that they are proposing. So more or less similar kind of vehicle where you lift the garbage bin and unload the garbage inside the vehicle, and then there it may be a compactor vehicle and it further compacts the garbage. So in this kind of this type of vehicle collects garbage from B type bins, and like for example it will go from each each society to society or each gated complex to another gated complex and keep on collecting the garbage. So it is able to collect garbage 50 bins in one trip. That means as per the capacity of the vehicles, it is able to take in 50 B type bins it can carry. So that means it has to travel to 50 bins first and then take this garbage to the landfill site and then return back. So it can travel along both major and minor roads. It has crew capacity of 2 and a capacity of 20 meter cube. Finally comes the smallest of the vehicles. It's a auto rickshaw type vehicle. It carries this is for collecting garbage from the C type bins, and it can collect garbage from 28 bins in one trip. So that is again as per the capacity of the vehicle. The capacity is 7.5 meter cube, crew required is 2, and it is usually for the congested areas. So as you can see, there is no specific system which is suitable for all areas. As per my area, as per my road network, as per the existing system that is there, we have to design our collection system. So how is the optimal routes generated? So first 8 hours of working is considered. So 8 working hours means once 8 hours is over, that means we have to use another vehicles, because beyond which people will not work. So the drivers will not work, the collectors will not work. So that means within 8 hours, one vehicle can collect only a certain amount of garbage. So if it is not able to collect from all the bins, we have to add another vehicle to the list, right? So in that way, we have to not only determine the routes for each vehicle, but also how many vehicles would be required and which vehicle will go to which area, right? So speed limit is considered same for all similar vehicles, and this speed limit is actually, or speed value is utilized to determine the travel time in each link as per the link's distance. So first, designing the routes for type A vehicles. The type A vehicles collects from type A type of bins, and first it starts from a garage it goes to the location of the first type A bin, and let us assume it's to be A1. And from bin A1, it goes to the landfill because it can carry only one bin at a time. It unloads the bin over there, then returns to the location of A1, places bin A1, and then travels to A2. So bin A1 to A2, and which sequence they will travel? Either it can go to the nearest one, or as per the input of the user, he can order the sequence in which he will travel from one bin to another. Or it could be as per a optimal plan, that is based on the location of all these bins, we can decide on the sequence in which this particular vehicle will travel from one bin to another. So that can also be done as we have done in case of earlier, that is there were community bin A and B. In the last lecture we discussed two community bins in which sequence we will go to which bin. So based on an overall optimal plan, we can also determine that. So finally it keeps on doing this and returning back to the same place, and then finally when the A1 AN or the final bin is completed, then it can return to garage. But as you can understand, there is working hours, travel time and loading unloading time that is required. So one vehicle may not be able to go to all the bins. So a cluster of bins with clearing order, that is with a sequence in which bin to go after which, that could be based on that optimal plan, are allocated to each vehicle. So this is the one thing, and the optimal path is generated for each vehicle. So as you can see, this is the optimal path generated for one of the vehicles. This is how it goes, and this is how the vehicle. So this is the garage location, this is where it starts, and landfill site is over here, and this is how the vehicle travels from different bins along the way. It will pick up and then will go to the landfill site. So the final result is vehicle number, there are 6 vehicles required. So each vehicle is used for certain time, 7 hours 20 minutes, 6 hours 91 minutes, 6 hours 58 minutes. It depends based on the location of the bins, based on what time the last bin ended, I may not have adequate time for another bin and so on. So, you can see that more or less all vehicles are utilized and only the last vehicle is utilized a little bit lesser. Total distance travel is also similar for most of the vehicles. The last vehicle is a little bit less, the last two vehicles are less, and number of bins cleared are also different. So, you can see that even though this has travelled for larger distances, the number of bins is less. So, because there is distance between these bins as well, right. So, in this case the bins may be clustered together, so that is why more number of bins could be collected. So, or these bins are located near to the the landfill site, that is why more number of bins are collected. So, for each condition we will get different set of number of vehicles, different routes for each of these vehicles and different time schedules for each of these vehicles. Now, coming to vehicle type B, like here I collect the garbage bins from different societies and all, and as we discussed it, we can go to 50 bins locations and then go to the landfill site. So, first we start from garage to location of first type B bin. This let us call it B1 and let us this bin be in cluster 1. So, what we are doing is we are creating a cluster of 50 bins, right. So, based on the nearness we can determine that in one area this cluster of bins should be taken care by one particular vehicle. So, bin 1 to bin 50 in cluster 1 as per optimal path within each cluster. So, I have 50 locations and the vehicle has to travel from one location to another to each of these 50 using the shortest path, and that we have to determine that it is not only the shortest path, it is the shortest route, right. Which sequence we will go? Should I go to bin 1 or then to bin 4, then to bin 8, or should I go bin 1 to bin 2, bin 3? So, it all depends on which sequence is the most optimal. So, from bin B50 then it goes to the landfill, then it unloads, then it again comes back and landfill B51 in cluster 2, then it starts working in the second cluster. So, we will repeat, we will keep on adding clusters still based on the working hours. Other vehicles for other remaining clusters, and of course, one vehicle cannot complete all the clusters because total bill number of this kind of bins is quite a lot. So, we have to add on other vehicles as well. So, joint optimization so that all bins, so sometimes here what we have discussed till now, that is we are finding the optimal path for moving inside a cluster. So, this is where we use something called a travelling salesman problem. It is called a travelling salesman problem. I will discuss that in detail. Now, this is exactly what we learnt in our previous slide, previous lecture, where we said that a vehicle starts from a depot, goes to two locations and we have to find the best sequence in which the vehicle should travel and reach the landfill site and again come back to the depot, right. So, this only thing is this vehicle can complete one cluster, return to the next, instead of returning to the depot, it returns to the next cluster, which maybe we can fix it, or we can also put in some time within that particular journey and we can say that this vehicle is made available after a certain time, then it could be engaged in another route, right. So, it could be a sequence of route for one vehicle as well. So, that is one. The other is we can do, we have the set of all bins in the city, we know the capacity of each vehicle and we can do a joint optimization where all bin locations and all available vehicles are taken together and using a vehicle routing problem, VRP, and then we can determine, instead of a travelling salesman problem, we can use a VRP to determine, we can use multiple vehicles, multiple routes to determine which are the best suitable solution for this particular area. So, we will explain VRP and TSP subsequently. So, over here you can see the collection is done in 3 days, every alternate day. So, 3 vehicles are required in the day 1 and you can see the time of travel is 9 hours for the first 2 vehicles, the last vehicle is little bit less and distance travelled is also computed and number of bins collected is also given. So, the first 2 vehicles collect from 200 bins, so they are able to do 4 clusters each, whereas the last vehicle just needs to go to and collect from 170 bins, right. So, in day 2 also similar values could be found out. So, maybe the day 2 the results are different, the day 3 results are different, it depends on the quantity of waste generated and so on. So, similarly For type C bins, we use type C vehicles. The C type bin clusters are formed for each A type bin. So first, for each A type bin, because C type bins are usually taken to A type bins, right? So for each A type bin, we find out which are the C type bins which would come to this particular A type bin, right? So that bin clusters are formed using C type bins which are assigned to each A type bin. First, visiting order of A type bins. First, we have to determine which A type bin I should visit first, and then next optimal path for each C type cluster is to be determined. So once I decide that I will start with this particular cluster, I find the optimal path within that cluster and I take the waste to the particular A type bin. Once that cluster is done, then I move on to the next cluster till my working hours is expanded. So it almost same as the last one that was done. So that here also it is done for 3 days, but I am only showing for day 1. You can see 6 vehicles are required, travel time for each vehicle, distance travelled, and number of bins covered by each of these vehicles. So this is the final results that we are getting. Now, how was all these things computed? How was this calculated? So in this work, these authors have used the software ArcInfo. This is a GIS software, as you know, and within ArcInfo there is something called a network module, and using this network module you can build a route network and then convert it into a link node diagram, and within that you can conduct the network analysis, and arc impedance is considered, speed of vehicle and road type, delays due to traffic jam, signals, one-way roads. These are all can be considered in the software, but here this study has not considered them. Time for loading, unloading at landfills and bin is taken at the node stop impedance. So as we have said that any node can be given some entry and end time, and this node stop impedance determines that how much time you spend at that node. Shortest path is computed following the traveling salesman problem, and network command paths, path and tour are used for finding minimum paths, right? So traveling salesman problem computes the shortest route, not the shortest path. Shortest path is determined by Dijkstra's, but a combination of multiple shortest path in sequence between different points, that's the shortest route, that is solved using a traveling salesman problem. So this traveling salesman problem is basically a distribution problem. In mathematics, it is known as or transportation, we call them as distribution problem, and we are determining the route for distribution of goods from the originating depot or a store to the consumers. So that's the starting of the distribution problem. In our case, routes for collection of solid waste from different community bins to the landfill site, right? So that's the representation of distribution problem in our context. Now this problem can be modeled using graph theory, same that we discussed in the last lecture, and we can use traveling salesman problem or vehicle routing problem to solve this particular this case. Now, what is the traveling salesman problem? It's a single route problem. We determine one route, like for example, here this is the starting point of the vehicle, and we are determining one single route which determines the shortest possible route that visits each demand point exactly once and returns to the originating point. Over here, I have gone via this particular route and then I have returned back to this particular starting point. I could have instead of going like this, I could have gone like this and so on, right? Then I could have gone here, and then this may be shortest path, may not be. So I don't know which sequence is the most, gives me the shortest path. So a traveling salesman problem actually determines the sequence in which we should go to each of this, and while we go from travel between each of these nodes, we use the shortest path between these particular nodes, right? So that is determined by a Dijkstra's algorithm. Ordering of reaching these points are given. So in which sequence we would reach these points, that is given. Number of there is no vehicle capacity limitation is also being considered in TSP, because one vehicle has to go and reach all these particular points. So there is no point of vehicle capacity restriction. Finds minimum traveling distance and cost for visiting fixed locations, and connects any two nodes with the shortest path. So between any two nodes, it's connected by a shortest path, right? So that's the traveling salesman problem. Now, what is a vehicle routing problem? It's a variant of the traveling salesman problem, where an optimal set of routes for a fleet of vehicles to serve a set of demand points from a originating depot. So, for serving this set of demand points, I may say that there is a vehicle capacity restriction. One vehicle may not be able to serve all points, or the capacity restriction could be in one route, one vehicle may not be able to serve all points. So, it has to make 3 journeys, or that means it has to conduct 3 journeys in 3 routes. Or if the time taken for each route is more than the working hours, then in that case I will require more vehicles, right. So, that is what the vehicle routing problem determines. It determines the optimal set of routes, that how many routes needs to be formed for a fleet of vehicles to serve a set of demand points from the originating depot. This is equivalent to multiple travelling salesman problem, where all salesmen have the same starting location. So, every vehicle is a salesman, it starts from this same point and it goes around and comes back to this particular point. So, how many vehicles are required depends on the time of start, the time of end, and if one vehicle can serve multiple routes, that can also happen. When the fleet size in a VRP equals 1, it becomes a TSP. And vehicle capacity limitation is also there. That is why when the capacity constraints of a route are taken into consideration, a TSP evolves into a VRP. So, anyway, we are not doing detailed estimates or calculations on how to solve all this, but at least you should have an idea that this could be solved via this kind of algorithms, right, this kind of problems in this particular ways. Now, the vehicle routing problem, as you can understand, that there could be several variants of this vehicle routing problem, and a variety of constraints can be considered, resulting in variety of variants or sub-problems. Now, in terms of solid waste management, these are some of the varieties which we can come across. One is called a capacitated VRP, where all collection points have to be served and the total waste quantity collected in each route is lesser than the capacity of the vehicle. So, this is a capacitated VRP, that means the vehicle has been given a capacity, so it cannot go to more points till its capacity is expanded, right. So, that is the first point. Then multiple depot VRP, that is waste collection points have to be served from several depots. That means instead of one depot, if I have multiple depot, so then how do the algorithm adjust itself, or how we can solve it. So, that is a variant of the standard vehicle routing problem. Then split delivery VRP, a waste collection point can be served by multiple vehicles if demand exceeds the capacity of a single vehicle. So, of course, if we have many collection points, but some of the collection points have 3 or 4 bins because it is a large collection point like a market and so on. So, in that case, it has to be served by multiple vehicles. So, how do I do the overall allocation of routes for all these vehicles with some points where these are common points where all vehicles will come? So, that has to be determined. Then stochastic VRP, where one or more components are random with an assigned stochasticity, like the waste quantity can vary over time. For the same point, the waste quantity may not be same every day, or the travel time along a corridor may not be same every day. So, if I introduce this stochasticity or this probability in the estimation, then what it means is every day the values are different. So, my optimization strategy has to consider that. So, that is called a stochastic VRP. Then VRP with time windows, which is waste collection points have to be served in chosen time windows. That means when I form the routes, there are constraints of at what time I can reach there. So, this is called a VRP with time windows. So, these are the different variants of the vehicle routing problem that could be adopted in waste collection studies. So, as you understand that this is the overall problem, but to solve it we require certain techniques or certain optimization techniques, because as you can understand there are many route options that are generated, but there has to be certain techniques to optimize it, right. So, as you understand, with increase in the number of demand points like community bin collection points, the TSP or VRP becomes exponentially difficult to compute using exact techniques. In the first slide, we have done exact calculations for each of the options available in front of us, and we can easily say that this is the smallest route. But when the options become very, very large, then exact techniques fails. There we require some heuristics, some certain rules or certain procedures, so that we can come to a problem solution at a much more faster pace. So, heuristics do not search the entire solution space, but employ problem specific strategies for faster search. So, that means heuristics are procedures to simplify the search process. Instead of looking into everything, We are based on certain criteria, based on certain strategies, based on certain system properties. We have to determine certain strategies to reduce this search space. So we can take certain decisions on that. Some of the classical heuristics algorithms are Clark and Wright savings algorithm. Then there is a two-phase algorithm or the local search method. Two-phase algorithm is, in the first phase, the demand points are clustered based on some distance criteria, and in the second phase, a TSP is used for optimize a route within each cluster. So that means this is a two-level problem. We break the problem into two parts. One is we cluster groups of solid waste management, solid waste collection bins. So within each group, we determine the optimal paths, like we did earlier with 50 bins, type B vehicles. We were showing that 50 bins could, a route for 50, going to 50 bins has to be formed. And then in which sequence we would visit the cluster, that is also determined optimally. So that's the second layer, the second phase of the optimization. In first phase, we find the optimal route among the cluster. In the second, we will determine the optimal route between the clusters. That means so it's a two-level TSP, you can say. Then local search method. Local search moves about the solution space from one neighborhood to another in search of the optimum solution. So problem with local search is we, in a particular distribution, sometimes some values are high, some values are low. But problem is, if I keep on focusing on a local area, then I may get stuck over there, and I may not find a higher value in some other zone of the solution, right? So anyway, so these are certain methods. But as I said that in local search, this problem happens that local search actually, brings you to some area where you're finding a highest value, but you are not exploring other areas where there may be a hidden higher value or a lower value, whichever you are searching for. So that means we can get stuck in some zones of the solution. So to overcome that, meta heuristics are being proposed. This overcome the problem of heuristic methods getting stuck in local optima by exploring further degrading solutions which help it to come out of the local optimum. So I have a solution, like this. So I am finding this is the minimum cost or this is the maximum cost, right? So this is the local solution I am talking about. I find that within this area, this is the one where I have got the maximum cost, right? So I say that this is the most optimal value. But in another area of this particular solution space, I see this value is even higher than this. So I am not able to go over there because I am stuck in this local area based on the strategies I have adopted. So instead, even though I am finding a higher value, I can say that I want to change this and move to another area randomly, right? So there are several techniques for that. One of the technique is like genetic algorithm. I find two good solutions. I combine these good solutions, generate an offspring. I take some good roots, in this particular solution and this particular solution, there is one root, there is another root. So I take some values from this sequence, some values from this sequence, and I make a new value. Then we again change it, give some amount of, this is known as the offspring, and from the offspring we can even do some amount of mutation and change that value, and then again start finding better solutions in this direction, right? So in this way we can use genetic algorithm. Similarly, there is taboo search. I maintain a list of searches that are there, which we say these are taboo, or this we will not search within a certain time, and then again we can go back and search in those particular areas. So there are different ways, or ant colony optimization, where the way ants follow other ants using pheromones. So similar kind of strategies are adopted to find the best solution out in a overall solution space. So anyway, there are classical heuristics, then there are meta heuristics, then there are exact methods. So it all depends on the size of the problem. If the problem is very large, we have to go and use meta heuristics to arrive at the final solution. So either you use TSP or a VRP, both of them utilizes any one of these algorithms, and in many cases, like as in ArcGIS software as that particular study has used, they use mostly the taboo search method, right? So in each software we will utilize certain strategies to reach the optimum solutions, right? So coming to the ArcGIS software, very quickly I will take you through this software. Like for example, in ArcGIS, it's a GIS software where there is this network analyst part. It's one extension or one component of this particular software which you can add, and using this you can do this vehicle routing problem. And this component is, you can do route choice, this is, then closest facility, service area, location allocation. There are different kind of things you can do which are part of, transportation analysis. One of them is vehicle routing, and to do that we have to add a network layer, and we have to set up the properties for the vehicle routing problem analysis, then create vehicle routing analysis layer, and then finally run the process to get our solutions. So, as you can see over here, this is the map of IIT KGP. This is the road network for IIT KGP. So, this is the GIS data for this. So, length of each road segment, the speed along that particular road, the time taken to travel along those road, the restrictions, is it a two-way road or a one-way road, all these things are given, right. So, first we have to create a network data set, and once that means using this particular shape file, we have to first create a network data set. Now, once we create the network data set, we have to take the values from that particular shape file, or from that particular table, you can say. If you are not aware of GIS, then from that table we will take the values, and we can set that, okay, in the network, in this particular link node diagram, finally also the travel time or impedance should be in minutes. That means that column in that particular table in the earlier slide, we have shown minutes for each link was given. So, that is taken as the impedance. Then restrictions, U-turns are allowed or not. So, all these values are taken up from the table, and finally we add for the restrictions, and then finally we create this link node diagram, or you can say this is the network layer that we are preparing. So, first converting the GIS layer of road network into a link and node diagram, and here also we can add those points for bin locations and all these things as well. So, once it is the network is prepared, after that we have to start a vehicle routing problem, and as we have said that we can do this with only one vehicle, in that case only for one route, in that case it would be a TSP, and first we have to generate the orders or the points from where your community bins should be, the depot, the route. So, these are the delivery location, and finally we have to run the solver, which actually gives us a solution for the route using that algorithm, that either any form of meta heuristics, most probably in GIS they use the taboo search. So, using that algorithm it will find the best possible route. So, we have to run the solver to get the route. Now, for each of the depot, for delivery location, for the order points means the community bins, right. So, we have to load the locations of each of these order points. As you can see, this is the start point, these are the order points, right. So, and then there are some restricted links are also given in red color. So, that means through these links we cannot travel. So, based on this we have to first create this load locations. For each load location there are time windows that could be given, the time taken that could be given, all these different properties could be added, which are properties of those for those nodes, right, node impedances and so on. Then finally we have to generate the route. So, as we can see in the previous slide, we also, one of the item was the route in this particular layer, and when we have, for this route, we have to first solve for this route, we have to give properties for the route, of course, like total travel time, certain restrictions could be given in terms of start time, end time and all this, and then we solve it, and once it is solved, you can see the schedule for that route is generated. You can see the vehicle in which direction the vehicle should go, what is the length of the route, what is the distance traveled, all these things are given, and the entire schedule is prepared for solid waste collection. So, over here you can see the route assignment and the schedule that is being generated, and this is the delivery location, the landfill site, suppose this is the start depot, and these are the points from where one vehicle will collect the garbage and eventually take it over here, and this is the shortest path which is being created, or the shortest route which is being created. And this shortest route is basically a combination of multiple shortest path among these particular collection points, and the sequence or the order in which I should go to this particular points gives me the shortest route via that, which is done via this traveling salesman problem. Now, The vehicle routing problem is just a variant of the traveling salesman problem where we can have multiple routes. Now, multiple routes could be assigned to multiple vehicles, or one vehicle can also do this multiple routes at different times of the day. So, here also you can see the solution. Order locations are given in red, depot location is over here. This is the delivery location of this garbage, and we have introduced two routes over here, and you can see one green and one yellow route. So, that means you can say this vehicle will first travel along this particular green route, complete its work, and then it will travel along the yellow route, or we can say two different vehicles will be traveling along this path if the time doesn't permit for one vehicle. But in IIT campus, the distances are very small, so one route will start like this. The capacity of the vehicle would be expanded within this particular set of bin locations, and then it has to start another route. So, which are the optimum routes that this particular solution will give? And as you can see, we have got the values for route 1, and similarly for route 2 also we have got, and we can get the total travel time, total travel distance, start time and end time for each of this particular route. For example, you can see the start time for the first route is 9 o'clock, ends at 10:43, whereas for the start time for the next route is 12 o'clock and ends at 2:18, right, 14:18. So, that means the same vehicle can be utilized in this particular in sequence. First, we will collect garbage from these bins. By the end of this, the vehicle will get filled. I will deliver that garbage to that disposal site, and again I will go to another route. I will start with some sequence, and as it is given, like for example, this is sequence number 1. I will go back to the depot. From there again I will start 1, 2, 3. In this way I will form another route and again go back to the disposal site. So, this is how this vehicle routing problem is solved using ArcGIS. So, of course, you can take a look at my earlier lecture, which is a little bit more in detail, and I have taken some of the resources from that particular lecture itself. So, this will give you a more thorough idea about this distribution problem, and so this is a transportation lecture, and you can always practice this in the software itself, and then eventually it will become clear. So, these are some of the references you can use. To conclude, route assignment and schedule generation for solid waste transportation vehicle requires detailed analysis since the potential for cost saving is significant, and appropriate model formulation for VRP is key to getting good solutions. Thank you.